Hi everyone, this is Savita Walsang and welcome to my channel Statistics Made Simple. In this video, chi-square test for goodness of fit solutions part 4, I'll solve another problem to check whether the binomial distribution is a good fit to the given data, which is a 5-marker, and will also solve problems based on fitting of a Poisson distribution and testing for goodness of fit, which would be 10 markers. Problem 8. To an observed frequency distribution, binomial distribution is fitted after estimating p from the observed distribution. Test whether binomial distribution is a good fit. So given to us is a table which has the observed frequencies and the expected frequencies. The observed frequencies are denoted by O and the expected or theoretical frequencies are denoted by E. So the observed frequencies are 3, 3, 17, 31, 28, 11, 1 and 2. The expected frequencies are 1, 7, 19, 27, 24, 13, 4 and 1. Let us start with the solution. The observed frequencies are nothing but the frequencies f. So within brackets highlighted in pink color, for the observed frequencies you write f. Then let us calculate capital N, which is nothing but the sum of the observed frequencies, which is equal to 96. Similarly, summation E also is equal to 96. So under solution, first write given small n is equal to 8. That is the total number of observations which we have in the table are 8. Capital N is 96 and alpha is 5% because it is not mentioned in the problem. Test for goodness of fit, the first step now is to define the null hypothesis and the alternative hypothesis. So H0 would be the binomial distribution is a good fit to the given data versus H1 binomial distribution is not a good fit to the given data. Now on the extreme left of this slide, I have listed down the observed frequencies and the expected frequencies as given to us in the problem. Now you'll observe that the first and the last two expected frequencies are less than 5 and we have to make use of the method of pooling. Expected frequencies which are less than 5 are highlighted in red color. Now whichever expected frequency is less than 5, it has to be pooled either with the succeeding or the preceding frequency to make it a value equal to 5 or a value which is greater than 5. So under the expected frequency column, 1 is added to 7 and we get 8, which is a value which is greater than 5. Similarly, towards the end, we add 1 and 4 and we get the value as 5. So the expected frequency is equal to 5. Now when we pool the expected frequencies, simultaneously the observed frequencies also should be pooled so that the number of frequencies in both the columns remain the same. So under the observed frequencies, 3 and 3 are added and you get 6. Similarly, 2 and 1 is added and you get 3. So form another table where you have the observed frequencies, the expected frequencies, then we calculate O minus E whole square and then O minus E whole square divided by E. So the observed frequencies are 6, 17, 31, 28, 11 and 3 and the corresponding expected frequencies are 8, 19, 27, 24, 13 and 5. Then calculate O minus E whole square. So 6 minus 8 is minus 2 square is 4. Similarly, 17 minus 19 is minus 2 square is 4. And the next value is 16, 16, 4 and 4. Then calculate O minus E whole square divided by E, that is 4 divided by 8 is 0.5. Similarly, 4 divided by 19 gives us 0.2105. take 4 places after the decimal after rounding off. The remaining values are 0.5926, 0.6667, 0.3077 and 0.8. Then calculate summation O minus E whole square divided by E, which is 3.0775. Next, let us write the formula of the test statistic. So under H naught, the test statistic is chi-square equal to summation O minus E whole square divided by E, which follows chi-squared n minus 1. So from the table, we get chi-square equal to 3.0775. Now the condition which is used to reject H naught is you have to compare the chi-square value with K2 value, that is the value from the statistical table. So if chi-square is greater than K2, then you reject H naught, otherwise you will accept H naught at alpha level of significance. Now the degrees of freedom for the goodness of fit test is actually n minus 1. Now we have pooled twice, so you have to subtract 2. And in the question, they have mentioned that the binomial distribution is fitted after estimating the parameter p. So whenever a parameter is estimated, again you have to reduce the degrees of freedom by 1. So we get 8 minus 1 minus 2 minus 1, which is equal to 4. So at 5% level of significance for 4 degrees of freedom, from the statistical table, we get K2 equal to 9.49. So the conclusion, since chi-square is 3.0775 and this is not greater than K2 equal to 9.49, at 5% level of significance for 4 degrees of freedom, we accept H naught and conclude that the binomial distribution is a good fit to the given data. Problem 9. Fit a Poisson distribution to the following data and test for goodness of fit. This problem would be a 10 marker. In the first column, you have number of accidents 0, 1, 2, 3, 4. The number of days are 21, 18, 7, 3 and 1. Now the first step is to mark the number of accidents as X and number of days as the frequencies, which are also the observed frequencies O. Then calculate capital N, which is equal to summation O, which is equal to 50. Now to fit a Poisson distribution, first we need to find out what is the parameter of the Poisson distribution. So lambda is the parameter of the Poisson distribution and it is not given to us in the problem. So we first need to find out the mean of the given problem and equate it to the mean of the Poisson distribution. So starting with the solution, first write given capital N is equal to 50 and alpha is equal to 5%. So capital X stands for the number of accidents. Now in the table, let us compute Fx. So you get 0, 18, 14, 9 and 4, which gives summation Fx equal to 45. Now calculate X bar, which has the formula summation Fx by n, which is equal to 45 divided by 50, which gives X bar equal to 0.9. Now equate the mean of the problem to the mean of the Poisson distribution, which is lambda. So we know that X bar is equal to lambda, which means that lambda is 0.9. Now that the lambda value is calculated and is 0.9, we can find out what is the PMF of the Poisson distribution. So in general, we know that the PMF of the Poisson distribution is P of x equal to, open the flower bracket, e to the power minus lambda, lambda to the power x divided by x factorial, where x takes value 0, 1, 2, 3, so on, 0 otherwise. Now, wherever you have lambda, replace it by 0.9. So you get P of x equal to, open the flower bracket, e to the power minus 0.9, 0.9 to the power x by x factorial, where x takes value 0, 1, 2, 3, so on, 0 otherwise. To fit a Poisson distribution, we need to find out the probabilities, that is P of 0 till P of 4, and then these probabilities are multiplied with capital N to get the theoretical frequencies or the expected frequencies. So let us now substitute x equal to 0 in the PMF. So you'll get P of 0 equal to e to the power minus 0.9, 0.9 to the power 0 by 0 factorial, which is 0.4066 into 1 by 1, which is equal to 0.4066. When x is equal to 1, we get P of 1 is equal to e to the power minus 0.9, 0.9 to the power 1 by 1 factorial, which is 0.4066 into 0.9 by 1, which gives 0.3659. Similarly, when x is 2, you get P of 2 equal to e to the power minus 0.9, 0.9 to the power 2 divided by 2 factorial, which is equal to 0.4066 into 0.81 by 2, which is equal to 0.3293 divided by 2, which is equal to 0.1647. When x is equal to 3, we get P of 3 equal to e to the power minus 0.9, 0.9 to the power 3 divided by 3 factorial, which is equal to 0.4066 into 0.729 divided by 6, which is equal to 0.2964 divided by 6, which is equal to 0.0494. Similarly, find out when x is equal to 4, what is the probability. So we get P of 4 equal to e to the power minus 0.9, 0.9 to the power 4 by 4 factorial, which is 0.4066 into 0.6561 by 24, which is equal to 0.2668 by 24, which is equal to 0.0111. Let us form a table where we'll write down the columns as given to us in the problem, that is the first two columns. So number of accidents is X, which is 0, 1, 2, 3, 4. Then number of days are denoted by F, or the observed frequencies O, which are 21, 18, 7, 3, 1. So capital N is equal to summation O, which is equal to 50. In the third column, write down the P of X values which you calculated, which is 0.4066, 0.3659, 0.1647, 0.0494 and 0.0111. The most important step now is to calculate the theoretical frequencies or the expected frequencies, which are denoted by Tx equal to capital N into P of X. So each probability is multiplied with capital N. So the first Tx value is 50 into 0.4066, which is equal to 20.33, and if we approximate it, we get 20. Similarly, the next value is 18.295, on approximation is 18, 8.235 is equal to 8, 2.47 is equal to 2, and zero point 0.5 is approximated to 1. So when we add 20, 18, 8, 2 and 1, we get the total as 49. But we should get the sum of the theoretical frequencies as 50. So now in this table we see that the sum of the theoretical frequencies in the fourth column adds up to 49. Hence we have to adjust one of the frequencies so that the sum is 50. Now carefully observe the values which are highlighted with the asterisks in pink color in the fourth column. So for the values marked with the asterisk, that is 20.33, the value after the decimal is 3. And then for 18.295, the value of the decimal is 2. And for 8.235, value after the decimal is 2. And for 2.47, value after the decimal is 4. Now, among the values after the decimal, that is 3, 2, 2 and 4, the closest to the number 5 is 4. So 2.47 is taken as 3 instead of 2. And so the final expected frequencies are written in the fourth column, which are Tx is 20, 18, 8, 3 and 1. So we get the total of the theoretical or the expected frequencies as 50. We have completed the first part of the problem where we had to fit a Poisson distribution and to obtain the expected frequencies, and this helps us to secure 5 marks. Now let us continue the problem by testing for goodness of fit. So let us write down the null hypothesis H0, the Poisson distribution is a good fit to the given data, versus H1, the Poisson distribution is not a good fit to the given data. Now write down the observed frequencies and the expected frequencies which we have obtained as shown in the extreme left of the slide. So the observed frequencies are the frequencies given to us in the problem, which are denoted by O, and they are 21, 18, 7, 3 and 1. So summation O is equal to 50. Then E values are nothing but the Tx values which we computed, that is 20, 18, 8, 3 and 1. So summation E is equal to 50. Now you will observe that the last two expected frequencies are less than 5, and these are highlighted in red color, that is the values 3 and 1. So we have to make use of the method of pooling. So the value 1 is added to 3 and you get the total as 4. 4 is still a value which is less than 5. So it is added to 8 and then you get the expected frequency as 12, which is a value which is greater than 5. Now the corresponding observed frequencies also should be added. So when you add 1 and 3 you get 4. Then 4 when you add to 7 you will get 11. Now form another table after we have done the pooling. So the observed values are 21, 18, 11. The expected frequencies are 20, 18 and 12. Then calculate O minus E whole square, which is 1, 0 and 1. Then find out O minus E whole square by E, which is 0 0.05, 0, 0 0.0833. So you get summation O minus E whole square by E as 0.1333. Under H0, the test statistic is chi-square equal to summation O minus E whole square by E, which follows chi-squared with n minus 1 degrees of freedom. So from the calculations in the table, we get chi-square equal to 0.1333. Condition which is used for chi-square goodness of fit test is you have to check if chi-square is greater than K2. If this condition is satisfied, then you have to reject H0. Now for testing of hypothesis, we require n for the degrees of freedom, and in this problem n is equal to 5, that is the number of independent variates. This is a very important step. Now the degrees of freedom is actually n minus 1, and because we have pooled twice, we have to reduce 2, and because we have estimated the parameter lambda, we have to reduce the degrees of freedom by 1. So you get the degrees of freedom as 5 minus 1 minus 2 minus 1, which is equal to 1. So at 5% level of significance for 1 degree of freedom, K2 value from the statistical table is 3.84. Conclusion: since chi-square is 0.1333, which is not greater than K2 equal to 3.84 at 5% level of significance for 1 degree of freedom, we accept H0 and conclude that the Poisson distribution is a good fit to the given data. Let us now solve the 10th and the last problem on chi-square test for goodness of fit. So problem 10. The following data relates to the number of mistakes in each page of a book containing 180 pages. Test whether the Poisson distribution is a good fit to the data. The problem is an important 10 marker. So in the first column we have number of mistakes as 0, 1, 2, 3, 4, 5, and number of pages are 130, 32, 15, 2, 1 and 0. Now the first step is to mark number of mistakes as X and number of pages as the frequencies F or the observed frequencies O. Then calculate capital N, which is summation O equal to 180. Under solution, first write given capital N equal to 180 and alpha is 5%. Then define capital X as number of mistakes. So to fit a Poisson distribution, we need the parameter lambda. Lambda is not given to us in the problem, and hence we need to find out the mean of the given problem. For that, form the third column in the table, which I have highlighted in pink color. So we need to find out fx. So the values are 0, 32, 30, 6, 4 and 0. And we get summation fx equal to 72. Now write the formula of the arithmetic mean. That is, we know that x bar is equal to summation fx by capital N, which is 72 divided by 180, and you get x bar equal to 0.4. Now we have to equate the mean of the problem to the mean of the Poisson distribution. So we know that x bar is equal to lambda. That means lambda is equal to 0.4. Let us now write down the PMF of the Poisson distribution. So the general format is P of x equal to, open the flap bracket, you have e to the power minus lambda, lambda to the power x divided by x factorial, where x takes the value 0, 1, 2, 3, so on, 0 otherwise. Now replace lambda with 0.4. So you get P of x equal to, open the flap bracket again, in the first line you will have e to the power minus 0.4. 0.4 to the power x divided by x factorial, where x takes the value 0, 1, 2, 3, so on, 0 otherwise. In the theoretical frequencies or the expected frequencies, let us now find out the probabilities for different values of x. So when x is equal to 0, in the PMF, put x as 0. So you get P of 0 is e to the power minus 0.4, 0.4 to the power 0 by 0 factorial, which is equal to 0.6703 into 1 by 1, which gives 0.6703. Similarly, when x is equal to 1, P of 1 is equal to e to the power minus 0.4, 0.4 to the power 1 by 1 factorial, which is equal to 0.6703 into 0.4 divided by 1, which is equal to 0.2681. When x is 3, we get P of 2 equal to e to the power minus 0.4, 0.4 to the power 2 divided by 2 factorial, which is 0.6703 into 0.16 by 2, which is equal to 0.1072 divided by 2, or you get 0.0536. Next, when x is equal to 3, P of 3 is e to the power minus 0.4, 0.4 to the power 3 by 3 factorial, which is 0.6703 into 0.064 divided by 6, which gives us 0.0429 divided by 6, which is 0.0072. When x is equal to 4, we get P of 4 is e to the power minus 0.4, 0.4 to the power 4 by 4 factorial, which is equal to 0.6703 into 0.0256 divided by 24, which is equal to 0.0172 by 24, which is equal to 0.0007. When x is equal to 5, we get P of 5 equal to e to the power minus 0.4, 0.4 to the power 5 divided by 5 factorial, which is 0.6703 into 0.0102 divided by 120, that is equal to 0.0068 by 120, which is equal to 0.0001. Let us now list down the probabilities and find out the theoretical frequencies. So in the first two columns, we'll write down the values as given to us in the problem. So number of mistakes are x, which is 0, 1, 2, 3, 4, 5. Number of days are f or o, that is 130, 32, 15, 2, 1 and 0, which gives capital N equal to summation o equal to 180. Then in the third column, which are highlighted in pink color, you find out or write down the values of P of x which we obtain, which is 0.6703, 0.2681, 0.0536, 0.0072, 0.0007 and 0.0001. Then we need to find out Tx, which is equal to capital N into P of x, that is the theoretical frequencies or the expected frequencies. Each probability is multiplied with capital N, which is equal to 180. So the first theoretical frequency is 180 into 0.6703, which is equal to 120.654, which is approximated to 121. Similarly, the next few theoretical frequencies are 48.258, which is approximated to 48, 9.648 is approximated to 10, 1.296 is approximated to 1, 0.126 is approximated to 0, and 0.018 is equal to 0. So when we add 121, 48, 10, 1, 0 and 0, we get the total as 180. So the final Tx values are 121, 48, 10, 1, 0, 0. So this part completes the first part of the question, that is you have to fit a Poisson distribution, and this would give us 5 marks. Now we have to check whether Poisson distribution is a good fit to the given data or not. So let us write down H naught. Poisson distribution is a good fit to the given data versus H1 Poisson distribution is not a good fit to the given data. Let us form a table on the extreme left of the slide, that is the observed frequencies and the expected or the theoretical frequencies. So the observed frequencies given to us in the problem are 130, 32, 15, 2, 1 and 0. And the expected or theoretical frequencies which we found out are denoted by capital E, that is 121, 48, 10, 1, 0 and 0. Now you will observe that the last 3 expected frequencies, that is 0, 0, 1 are less than 5. So we have to make use of the method of pooling, and these expected frequencies which are less than 5 are highlighted in red color. Let us now add 0 and 0. You get 0. It is less than 5. So 0 is added to 1, which is equal to 1. Again, it is a number which is less than 5. Then this 1 is added to the number 10 and you get 11, which is a value which is greater than 5. So similarly, add the corresponding observed frequencies. So 0 plus 1 is 1, 1 plus 2 is 3 and 3 plus 15 is 18. Now write down the observed and expected frequencies which we have obtained after pooling. So the observed frequencies are 130, 32 and 18, and the corresponding expected frequencies are 121, 48 and 11. Then calculate O minus E whole square, which is 130 minus 121, which is equal to 9. 9 square is 81. Similarly, the next O minus E whole square value is 256 and then we have 49. Then calculate O minus E whole square by E, which gives 0.6694, 5.43s and 4.4545. Therefore, you get summation O minus E whole square by E as 10.4572. H naught, the test statistic is chi-square equal to summation O minus E whole square by E, which follows chi-square with n minus 1 degrees of freedom. From the table, after the calculations, we have got chi-square as 10.4572. The condition for chi-square test for goodness of it is here to check whether chi-square is greater than K2. If this condition is satisfied, then you reject H naught, otherwise you accept H naught. So now for testing of hypothesis for the degrees of freedom, we need the value of n. So for this problem, n is equal to 6, which stands for the number of independent variates. So the degrees of freedom is n minus 1, and we have pooled thrice, so we have to subtract 3, and we have estimated the parameter lambda, so you subtract 1. So you get 6 minus 1 minus 3 minus 1, which is equal to 1. So at 5% level of significance for 1 degree of freedom, K2 is 3.84. Conclusion: since chi-square is 10.4572, which is a value greater than K2 equal to 3.84 at 5% level of significance for 1 degree of freedom, we reject H0 and conclude that the Poisson distribution is not a good fit to the given data. So by completing this step, we will get the remaining 5 marks. So the total marks for this problem is 10. As I've already mentioned, the chi-square test for goodness of fit is a very important topic. We have learned three different types of problems in this category. The first type was where they use the words like equi-probable or equidistant or uniformly distributed. The second type is where they give us a ratio. And the third type, which is for 10 marks, is where we fit either a binomial distribution or a Poisson distribution and then test for goodness of fit. So practice all these problems thoroughly. Thank you all for watching and look out for my next video where I'll explain the procedure for chi-square test for independence of attributes, which is again an important topic, and you get problems for 5 marks.